This lecture we will start the unit number 5, that is design of a synchronous machine, and we will discuss about the constructional features, output equation and main dimensions of the synchronous machine. So in this lecture we will cover the points like types of the synchronous machine, constructional overview of the synchronous machine. So like the induction motor, the synchronous machine is also having the two main parts, that is a stator and rotor, which one is stator is the stationary and rotor is rotating part. And the stator rotor is all having the two types, salient type rotor and non-salient type of rotor. So in this lecture we will discuss in short about the stator and both types of rotor. The synchronous machine is called as synchronous machine because the rotor of the synchronous machine is always rotating at the synchronous speed. Then we will discuss about the output equation of the synchronous machine, choice of the specific electric loading and specific magnetic loading, along with the separation of main dimensions. So first we will discuss the about the types of synchronous machine. Now the synchronous generators are broadly categorized into three types: hydro generators, turbo generators and engine driven generators. Hydro generators are those generators which are driven by the hydraulic turbines like the Francis turbine, Kaplan turbine or Pelton wheel turbine, and usually these generators are run at the speed below the 1000 rpm. Turbo generators are the steam driven generators, and these are the high speed generators which are usually rotate above the speed of 1500 rpm. Engine driven generators are the generators which are driven by the IC engines, and the generators are run at a speed less than 1500 rpm. Now like the induction motor, the synchronous machine is also having the two main parts, stator and rotor, and there are two types of rotor depending on their construction. One is the salient pole type of rotor and another is non-salient type of rotor. And according to which type of rotor is used in the synchronous machine, the synchronous machine is classified into two categories, namely salient pole machine and non-salient pole machine. The salient pole machine is having a projecting pole rotor with a concentrated field winding, and because of the projecting poles, the salient pole rotor is used in the low speed generators, which are normally the hydraulic generators or the engine driven generators. But in the non-salient pole, the rotor is a cylindrical smooth rotor in construction, so therefore it is also called as smooth cylindrical rotor. And this rotor construction is employed for the mechanical driven by the steam turbines. Now let me discuss about in short about the construction of the synchronous machine, first we will discuss about the stator. The stator is the stationary part of the machine, and which is the outer part of the machine, which consists the frame called as yoke, and the stator core, whose main function is to provide the path for magnetic flux. So along with the winding housed in the slots of the stator. Now the yoke is acting as a protecting cover, which is a outer frame of the machine, whereas the stator core performs the function to provide the magnetic path. And in order to reduce the eddy current loss, like the induction motor, the stator core is also laminated with the thin stampings. Now let me discuss about the rotor. A rotor carries the field winding, which is supplied by the DC source, which is known as the exciter. And as I already told that there are two types of rotor depending on their construction. One is the salient pole type and another is the non-salient pole type. Now in short, let me discuss about these two types of rotor. The first we will discuss about the salient type of rotor or the salient pole rotor. So you can see in the figure, it is very clear from the figure that the rotor is having the projecting poles, which are mounted on a large circular steel frame, which is fixed with the shaft of the generator. And this construction of the rotor is cannot be made strong enough to withstand the mechanical stress at high speed, and because of that, this type of rotor is usually used in the alternators which are running at either low or medium speed. So that's why the salient or projecting pole type of rotor is usually used in either hydro generators or the engine driven generators. But the non-salient pole rotor is a smooth cylindrical outer periphery. Now you can see the construction of the rotor. Then it has a smooth cylindrical outer periphery with the number of slots, and the field winding is housed in these slots, which is energized by the DC supply. And this construction of the rotor is having a mechanical robustness, and therefore the rotor can be used for the high speed alternators, which is normally a turbo generator. So the non-salient type of rotors are usually used in the high speed alternators or the turbo alternators, which are steam driven alternate turbines. Now let me discuss about the output equation. The output equation of a synchronous machine is the same as that of the induction machine. Already we have gone through the output equation of induction motor, and the output equation of the induction motor is the kVA is equals to CO d square L into N, where in this equation kVA is the input power rating, CO is the output coefficient, D is the diameter of the stator core, L is the length of the stator core, and the N is the speed in revolutions per second. So the same equation we are using in the synchronous machine also. So the output equation of the synchronous machine is the kVA is equals to CO into D square L into N, where in this the equation the output coefficient CO can be determined by using the 1.11 kW BAV AC pi square into 10 to the power minus 3. The kW is the winding factor, BAV is the specific magnetic loading, and AC is the specific electric loading. Now the output equation can be worked out in terms of the peripheral speed also, as we know that this peripheral speed is the V is equals to pi d into N. So from this equation we can write the value of the d as V divided by pi N. Now if you put this value of the d in the equation of the output kVA, then we can write here the kVA equation as CO, the value of the CO is 1.11 into kW into BAV into AC into pi square into 10 to the power minus 3 into d square. The d square is equals to V, d is having here the V divided by pi N. So if you take the d square here, then the V square divided by pi square into N into L into N. So if you take this equation here, then this N and N gets cancelled, pi square and pi square gets cancelled. So the equation of the kVA becomes the kVA is equals to 1.11 kW BAV AC into 10 to the power minus 3 into V square N divided by N into L. So in terms of the peripheral speed, the output equation of the synchronous machine can be written like this also. Now let me discuss about the choice of specific loadings. So first we will discuss the choice of specific magnetic loading. So like the induction motor, the kVA or output equation of the synchronous machine is also same. That's why the size and the cost of the synchronous machine is also depending on the specific loadings. And if we are increasing the specific magnetic loading and specific electric loading, then the size and cost of machine becomes reduced because these terms are inversely proportional to each other. So the higher values of the specific magnetic loading and specific electric loadings are always preferable, but the specific magnetic loading and electric loading both are influencing the other performance parameters of the synchronous machine, and that's why the proper choice of the both specific magnetic and electric loading is very important. Now the specific magnetic loading influence the three factors: iron loss, voltage, and the short circuit current. Higher value of the specific magnetic loading means actually the higher value of the flux density, and higher value of the flux density is nothing but the higher value of the flux in the iron parts, which increases the iron loss like the hysteresis and eddy current loss and affects on the efficiency. Therefore, if the specific magnetic loading is higher in value, then we need to compromise with the efficiency. Second is the voltage. Higher value of the specific magnetic loading is nothing but the higher value of the flux density in the teeth of the rotor, stator core. And along with the high flux density, if we want to design the machine with a higher voltage, then the insulation required becomes higher, which occupies a large space. So the size and cost of the machine becomes increasing. And the last major factor which influenced by the specific magnetic loading is the short circuit current. Higher value of the magnetic loading is nothing but the higher value of the density, which results in the decrease of leakage reactance, and the reactance is acting as a opposition to the armature current under the short circuit condition. Hence, if the leakage reactance becomes decreased, then the value of armature current under short circuit condition becomes increased. And because of these three disadvantages, there are always certain limitations to select the higher value of the specific magnetic loading. And that's why usually the value of the specific magnetic loading is selected between 0.55 to 0.65 for the cylindrical rotor machine and 0.5 to 0.65 for the salient pole machines. So, if in the example it is not given, then you can assume the specific magnetic loading between these two ranges for a particular type of rotor or machine. Now, the choice of electric loading. See, similar to the choice of the specific magnetic loading, the choice of electric loading is also very important, and the specific electric loading affect the factors like the copper loss, voltage, and the stray load losses. Obviously, if the electric loading, that is ampere conductor per meter, is higher in value, then the current in the armature becomes higher, which causes the large copper loss and results in the temperature rise also. So, ultimately the reduction in efficiency. And higher value of the AC, that is the specific electric loading, can be used for the low voltage machines, since the space required for the insulation will be smaller. And with increase in the higher specific loading, electric loading, load losses will also increase. And because of that, the choice of the specific electric loading is between 50,000 to 1 lakh for the turbo machines, that is high speed machine, and between 20,000 to 50,000 ampere conductor per meter for a salient pole machines. Now, let me discuss about the separation of main dimensions. Once we calculate the product d square L from the output equation, the next step is to separate the d and L from the main dimension, from the d square L product. And usually the d is influenced by the peripheral speed and the type of the pole construction. So, if the pole is bolted in construction, then allowable peripheral speed is 50 meter per second. So, by taking this 50 meter per second allowable peripheral speed, we can calculate the value of the d. And if the pole is having the T head construction, then the allowable peripheral speed is 80 meter per second. Along with the constraint of the peripheral speed, there are certain other constraints which we can use to separate the main dimensions from the product d square L. Like, if the round pole is used, then for the round pole, the ratio of core length to pole pitch is 1 to 3. So, simply the ratio L by tau is equals to 1 to 3. And along with this, if for the round poles, if we consider the pole is a square pole face, then the length of the stator core L is equals to the pole arc. And for a rectangular pole, the ratio of pole arc to the pole pitch is 1 to 3. So, by taking these constraints, we can separate the main dimensions d and l from the product d square l. Further in detail about the separation of main dimension we will discuss while solving the examples in the next lecture. Thanks for watching.